All right, this is part two of the right ventricular function in the ICU series. Now we're going to talk about estimating RV size, looking at systolic function and systolic pressures of the RV. So we're going to start with our most critical view of the RV, and I've kind of put these in what I consider to be the descending order of importance from most important to least important in the ICU at trying to understand right ventricular function and pulmonary hemodynamics. So we'll start with the apical four-chamber. It's my favorite. For looking at this stuff. I've mentioned that before. Remember, when you're looking from the four-chamber view, you're trying to get something like this. This is a little off axis, but you want to try to get some of that lateral free wall of the RV. And a couple different ways to try to pick that up. So here, let's just look at a very simple example to start. You might recognize that this is an eponymic RV dysfunction finding an echo called McConnell sign. So here we're looking at the RV and pretty decent four-chamber view. And the lateral free wall here is what we're looking at. Obviously, apex is squeezing, but lateral free wall is really pretty much not moving at all. So that's really the first step of our assessment of right ventricular function, is trying to get this four-chamber view and making a qualitative assessment of the right atrial size, right ventricular size, and right ventricular function. Now, sometimes it's hard to see the free wall, and there actually are a few different ways to try to turn your probe, angle your probe, move your probe around the apex to pick up the RV a little bit better. In this video here, this is called an RV modified apical four-chamber view. This is pretty good for free wall visualization. One of the problems is, though, is if you cut it the wrong way, you end up overestimating the RV to left ventricular ratio. So you can see early in this clip that the RV looks much bigger than the LV, but then when I get, there's a couple slices here where the axis changes a little bit, and the RV actually is probably smaller than the LV. They're both still very dilated, but you might overcall RV size here in this modified apical four-chamber view. One of the nice things about this is sometimes it's really, really great for picking up TR jets, which we'll talk about more in a moment. So this modified view often gives you the best angle, right? You want, a pretty straight line through the tricuspid valve. This often gives you that best angle to pick up that RV to right atrial systolic pressure gradient, also known as a tricuspid valve regurgitation jet. And as you can see here, we actually have what looks like a pacer wire or a catheter, probably a pacer wire, I guess, since it's going in the RV, traversing the valve. And you can sort of imagine putting your Doppler through there and picking up a nice TR jet. Down in this corner, I have what's called the RV focused apical four-chamber view. Now, this is not good for lining up your TR jet, but it is great for free wall visualization. The other thing it's really nice for is measuring the RV diameter at this basal segment just below the tricuspid valve. So sometimes you want to move laterally and really work beyond the left ventricular apex and look at the right ventricle through the left ventricle, using your left ventricle as your echo acoustic interface so that you can pick up this lateral free wall really nicely. So that's one of the shortcomings of this modified apical four-chamber view. The free wall can kind of come in and out of view. So sometimes you can get a decent view of it here, but sometimes moving more laterally and looking through the left ventricle, you can get a better sense of what the free wall is doing. So anyways, those are both different ways of making qualitative assessments. So when we're talking about assessing RV by size, depending where you look, these are sort of general guidelines as to whether or not RV dilation is present. So if the right ventricular to left ventricular size ratio is less than 2/3, that's normal. There's no RV dilation. If it's somewhere between 2/3 to 1, that ratio, it's mild. Once the RV is about the same size as the LV in an apical four-chamber view, then we're talking about moderate RV dilation. And once it's greater than 1, with apical displacement, which we sometimes will see in this McConnell sign where the RV is so dilated that it starts to occupy the apex, then we're talking about severe RV dilation. If you want to quantify it, probably the best place to measure is at that RV basal segment at the level of the tricuspid valve, and you should measure a diameter there of less than 4 centimeters. Anything larger than that is considered dilation. You can also measure the RV at the mid-cavity in the apical four-chamber view. I don't routinely do that, but that'd be the other place to measure it. I'm usually doing some sort of qualitative assessment. And again, you're often making these measurements in the RV-focused apical four-chamber view, where it's actually easier to sort of pick up the free wall and see where it's delineated. All right, moving ahead. What else do I do in this apical four-chamber view? Well, I want to measure RV systolic contractility in some way. And in order to do that, I'm going to take advantage of the fact that, as we discussed, the RV has these longitudinal myocardial fibers that contract from base to apex. And I can actually just look at my tricuspid annular plane and see how well it's moving toward the apex to get a sense of RV systolic contractility. So we have two measures for that. One is done in Mmode, which is tricuspid annular plane systolic excursion. You've probably heard of this before. It's called TAPSE. And the other is just doing tissue Doppler of the same area. So that's what I have here, and it's an S prime velocity. I put my tissue Doppler right over this annular plane where the right atrium meets the right ventricle and the valve inserts into the myocardium, and I'm going to watch how that moves toward the apex in systole. So both of these things are really predominantly looking at the tricuspid valve annulus. So here's how you're going to line up your TAPSE. This is again that McConnell sign we saw before. I'm going to get my Mmode and I'm going to just put it right through this annular plane. And again, I'm trying to see how well these longitudinal fibers are pulling the base of the heart, the RV, toward the apex. And when I look at my Mmode over time, remember Mmode is just measuring a single point on the echo screen over time. I'm going to see that this tricuspid annular plane moves much closer to the base with systole and then falls back during diastole. Now this is in the same patient we saw in the last one. You can tell this TAPSE is actually quite good if you know anything about TAPSE. So during systole, there's this huge rise, and this is how I measure it. I'm going to pick this point and this point here, the trough and the peak, and it's going to give me a TAPSE. This is a TAPSE of 23 millimeters or 2.3 centimeters, which is actually very good. So anything above 20 millimeters is clearly normal. Most references, in fact, almost all will say anything above 16 is still considered normal. And the cutoff under 16 is where it starts to get a little hazy. If you're talking about TAPSEs less than 10 millimeters, it's very diminished. And then when you're between 13 and 16 or 11 and 13, they're both kind of pretty bad RV function. So remember, this is just a linear measurement. This is simply movement of that plane towards the apex, but it tells you a lot about right ventricular contractility based on the way that right ventricle is structured. We said the other way to measure this was with tissue Doppler, and we're measuring what's called the S prime velocity. And this is my tissue Doppler tracing. These are my big systolic excursions. So that's what I'm going to measure here. This is the same patient as the last screen. So this correlates well. This is an S prime of 17. That's very clearly normal. And as we saw, the TAPSE was 23 millimeters, very clearly normal. This patient has very good right ventricular contractility. And in fact, when S primes are above 12, if you're thinking that the patient might have an RV infarct or you're worried about significant RV strain in the context of acute PE, these S prime velocities of 12, 13, 14, once you get above that, you're pretty confidently ruling out significant right ventricular dysfunction. Now, these are just rough measures of RV contractility. The gold standards are things like RV 3D echo or RV MRI, but we're trying to get good estimates of these parameters with just simple ways to measure it at the bedside in the ICU. Okay, so let's take a look at this patient. Pop quiz, what is this patient's right ventricular systolic function based on what I've told you should know? So here I'm again measuring a TAPSE. You can almost see from this still image here that the RV looks pretty big compared to the LV. Now maybe a little off axis, you would want to watch this video, but you can see the RV is a little big. And here my TAPSE from my trough to my peak is only 12 millimeters. And then my S prime velocity for my tissue Doppler imaging here, I'm going to measure at 7.5 centimeters. So is this normal or depressed? Yeah, if you're paying attention at all, TAPSE under 13, clearly depressed. S prime velocity in the single digits, clearly depressed. RV systolic function is going to be clearly depressed in this situation. So that's RV contractility. We can learn a little bit now about RV systolic pressure if we decide to look at our tricuspid jet and measure the velocity. Now, you're going to measure tricuspid jets actually from multiple views because you just want to try to find the angle at which it's going to give you the highest velocity. But when you're in this apical four-chamber view, you better be looking for it because it's often one of the best places to pick it up. So first, I'm obviously going to actually want to color the jet, and then I'm going to use my continuous wave Doppler to actually measure the velocity. You want to place your sample area where the jet is maximal, but we're going to reserve judgment on the severity unless it's clearly severe. Again, we want to look at jets in multiple views before we say this is a bad jet, this is bad TR. But we can always measure velocities in any view. So here I'm in an apical four-chamber view again. This is again more of like a little bit of a modified RV focused apical four-chamber view because I really want to get my jet to come out. I've got my color box here already, so I'm watching the jet. I started with a pulse wave, I switched to continuous wave, and I'm going to place it right where that jet is maximal. So let's watch that again. Wrong Doppler mode. Now this is continuous wave. I'm going to place it right where that jet is maximal and try to pick it up. Again, it's continuous wave Doppler. And I'm not going to call this severe yet unless I'm convinced it's severe. Now this looks pretty moderate, I would say. You can see the jet is occupying probably at least a half of the right atrium, if not up to 2/3. Hard to say. Probably a mild to moderate jet here. But if I wouldn't say this is non-severe until I've looked at multiple different angles and said, okay, I don't find severe TR in any other view. Now, when I measure my TR jet, I'm going to take advantage of the modified Bernoulli equation. Sorry if you're familiar with the Bernoulli equation. If you're not, it's a beautiful, simple, but outstanding way to understand hemodynamics. And the modified Bernoulli equation tells us that we can understand what a pressure gradient is between two chambers of the heart if we know the velocity between the two. Very simple. And the way that those two are correlated or measured or equal or put into an equation would be as follows. Delta P, the pressure gradient between the two chambers, is equal to 4 times the velocity squared. Now, when we're talking about right ventricular systolic pressure, we're going to be looking at a pressure gradient from the right ventricle to the right atrium. So I'm going to be looking at my TR jet. That jet signifies right ventricle to right atrial pressure gradient. Does that make sense, right? Right ventricle shooting into the right atrium, I can infer the pressure gradient if I know the velocity through the jet. So in this example, I've picked up the jet multiple times very nicely, and I've measured the biggest one on the screen. So my maximum velocity here was 3.3 meters per second. So we can solve this now, right? In this case, my modified Bernoulli equation, 4v squared equals 44. So all I did was put 3.3 in here, squared it, multiplied by 4, and I get 44. All right, so were you paying attention? What is this? What is the correct interpretation of this value, this 44? Is that my PA systolic pressure? Is that my RV systolic pressure? Is that my right atrial pressure? Gosh, I hope you don't say that. It's actually none of the above. It's telling me the gradient between the two. It's not telling me the absolute value of the right ventricular systolic pressure. So remember, it's a pressure gradient. So if I wanted to know the right ventricular systolic pressure, I actually have to know what my right atrial pressure is as well. This 44 is the difference between the two during systole. But I have to add in my right atrial pressure to actually estimate my right ventricular systolic pressure, which we'll come back to as we revisit this in some cases. So we've kind of knocked out the big stuff from the apical 4-chamber view. Now let's take a look at the RV inflow view, which is a beautiful view of the TR jet often. And this is a great place to look at TR jet severity. So in this video, I tried to show you how I move from a peristernal long axis view and start to pick up the RV inflow view. It takes a little bit of rotation of the tail of the probe. It's about a 10 to 15 degree clockwise rotation from the peristernal short axis view. And as you can see in this video, I'm going to start here. You know, it's not labeled correctly at the start. You'll see. Just wait a minute. But my aortic valve is here, left atrium's here, left ventricle. And as I start to spin the probe, my aortic valve starts to fall out of view, and I end up getting my right ventricle wrapping around here with my tricuspid valve and my tricuspid inflow view. And I started to get this view from my peristernal long axis view, some rotation. Sometimes you have to slide up a rib space to pick this up. But this is just, I could tell you about it all day long. It's just something you have to go grab a probe and try doing. But the beauty of this is that this is often giving me some of my best jets, right? So I may not see this jet very well. If this is an inferiorly or posteriorly directed jet, I may not see it very well in some of my other views. So this is why I always double check TR jets in every view. So again, I would just use the Bernoulli equation. This is a patient who looked like they have a decent jet, but actually you can see the velocity isn't terribly high. So I measured in this patient the max velocity in of my tricuspid regurgitation is 1.8 meters per second. So I can throw that into the modified Bernoulli equation, get a systolic pressure gradient. So my RVSP, my RV systolic pressure, is going to be that gradient plus whatever my right atrial pressure is. Now, most machines are cool that they actually do the modified Bernoulli equation for you. So in this machine, the machine just spit up the pressure gradient was 19. So I know my RVSP, RV systolic pressure, is 19 plus whatever my right atrial pressure is. And I can measure that. If I have a central line in place, I can infer that from looking at the IVC in my hepatic veins. But I know that my right ventricular systolic pressure, if my right atrial pressure isn't very high, then my right ventricular systolic pressure actually is pretty normal in this patient, even though they have a significant TR jet. So the reason to measure this in multiple views is because the Doppler shift is related to the cosine of the angle at which you're acquiring the signal. So, you want to try to get a view at which the jet lines up best. So if I went back to the previous view and I showed you this jet again, you could see that if I line up my probe here, I'm going to be pretty close to 0 degrees between where the probe is to where this Doppler signal is going to be picking it up. And as long as I'm within 20 degrees, my error for the velocity that I'm calculating is within 5 to 6%. Once you start to get off axis by more than 20 degrees and you're trying to do Doppler, that's where you start to get significant measurement errors.